Hello, this is Dr. Nuray Kayakol speaking. The title of my seminar is How to Specify Boundary Conditions of CFD Simulations. Here is the agenda. First, I will describe boundary conditions for internal and external flows. Specifically, I will talk about inlet and opening settings for CFX. Then I will explain how well-posed boundary conditions can be selected. I will show you a CFD application using CFX. So in order to describe this case, I need to mention some information about turbulence and finite volume method. Here is the boundary types. Safety engineers are well familiar with inlet, outlet, wall, and symmetry boundary conditions. CFX user can define inlet and outlet, any of them, by using opening type boundary. This is a kind of a boundary that flow may in or out. So I will describe all these things in detail. So until now, suppose that you choose your boundary types. So what are you going to define as a value? So you need to give information about flow regime, mass and momentum, heat transfer, and turbulence. So any boundary condition should have some information about this. So you might not think that only giving some parameters for mass and momentum like velocity or mass flow rates. So if you don't touch any other things, that means program will run with default values. Actually, this presentation just remind you what will be the default values of softwares. So let's start talking for internal flow. You see simple pipe flow. You have one inlet and one outlet, and the surface of the pipe is a wall. These settings for full geometry. In CFD, we can reduce number of grids and also CPU time just by using half of the geometry. Then this line represents the symmetry, actually the plane where we cut the pipe into two. So it's not necessary, of course, to define outlet as opening, but this is an option. So when we use some portion of the geometry, we use boundary condition as symmetry. So this can be also given an example from a book, Verstik and Malala Sekar. I strongly suggest for beginners to go over this book. So this screenshot from one page related to boundary conditions. So what you see is a rectangular geometry. You might think this is also a pipe. So solid walls is shown with this regular pattern. So inflow and outflow boundary, flow in this direction. So okay, so you have chosen the boundary types, but what you are going to define at those boundaries. For the inlet, you can give velocity and density for flow calculations. If you are also solving the energy equation, you need to give value for the temperature. For the solid wall, velocity, of course, is equal to 0. If you know temperature or flux, you can define. as a boundary condition. Here is an example for external flow. You see a rocket inside of a tunnel, like a wind tunnel. So the box enclosing these solid objects, certain dimensions, so that flow can be simulated without any restriction. So inlet, you see much close to rocket, because flow will come and move around the rocket. In this object there are some how can I say, wings will disturb the flow and create vortices behind the rocket, so outlet is much far from the object. So this is a typical geometry and enclosing box or tunnel over a rocket. So similarly, this is also another screenshot from the book, CFD book. In this case, this is the solid object and there is a box around it. So here an inlet and outlet, but this time you see that top is open, top and bottom has open boundary. That's the flow in and flow out. By the way, I think this is a mistake. The direction of flow should be opposite anyway. So in this time you define velocity, temperature, or density at the inlet of this tunnel, and the solid object becomes a wall. Of course, velocity is 0. If you know the temperature or heat flux, you can give as a boundary condition value. Okay, let's start talking about first what we mean by the inlet. So what are we going to define at those boundaries? For incompressible flow, if the velocity is measurable, you can use it as inlet value. For incompressible or compressible flow, you can use pressure or mass flow rate. So these are possible value we can define at the inlet. Let's see boundary condition settings for inlet. As you see, there are many options because CFD codes are general purpose codes, so it should serve for many users. For inlet boundary condition, there are 4 different types of information we should give. First one is the flow regime. The second one, mass and momentum, heat transfer, and turbulence. So when you define boundary condition for inlet, perhaps you just give velocity values and then press apply and do the other settings. Actually, you see there are many things. If you don't touch other options, that means you run your case with so many default values. Let's see one by one what we mean by flow regime. By the way, these settings for CFX, you might see different names, perhaps other things in Fluent. So think that this lecture is about the use of not Fluent, which is commonly used, but this is for CFX. In CFX, first of all, you have to define whether your flow is sonic or subsonic. That means you will divide your velocity with sound velocity, so you can decide whether your system subsonic or sonic. In the mass and momentum section, you have 1, 2, 3, 6 options. You can either define velocity or mass flow rate or pressure, either static or total pressure. You might give one single value for velocity, or you can define Cartesian components, velocity components, if you work on Cartesian coordinates, or in cylindrical coordinates, maybe you will give some other velocity components. We will see all these in coming slides. In left hand side is mainly for flow values. For the right hand side, first thing is the for heat transfer. You see, similar to pressure, you can define static temperatures, total temperature. If you know the enthalpy, you can define. The third one is the turbulence. This is not about defining turbulence model, but CFX asks you some information about for turbulence stuff. If you don't know anything about the details of turbulence features of your system, at least you have to define first three, the amount of turbulent intensity. So I will describe this later on. Let's talk about mass and momentum section. Suppose that you are working on cylindrical components. What you have to do, you need to give axial, radial, and theta component. So there are also some other things to define your system. I will not go over all these details, but I want to show you if you use this kind of commercial software, you need to know all the details of inlet conditions. If you don't define anything, that means you are using default values, just to remind you. So this is for cylindrical settings, and then Cartesian coordinate. Instead of giving one single value, you can give component in x, y, and z directions, the value of velocities. So perhaps maybe in a uniform flow you can define one of these values. Now we finished the velocity part. So instead of velocity, we can define mass flow rates. If it is a measurable quantity, you can use it, but beside this value, you need to define flow direction. Think about m dot is equal to rho v bar n s. That is the density multiplied by average velocity and then area, cross-sectional area. So here a program can calculate velocity from mass flow rate, but you need to tell the direction so that it can calculate velocity in x, y, z direction. So one of the option is the normal to the boundary condition. If you know, you can define other components. Mainly we leave it as it is. Normal to boundary condition is a good option. How about the opening? Opening is different than inlet or outlet, so you can define both inlet and outlet as opening. The only thing is, if you define an inlet as opening, that means outflow is possible, just opposite for the outlet. But the definition is not different than the inlet. This is how velocity of opening is defined. Maybe the nomenclature is different, but this is nothing but velocity in XYZ directions. Also, the pressure is this, similar to outlet pressure, so you can define whatever you want. Just you need to know that opening is not different than the outlet boundary condition. The only thing, it is better to use opening if there is a recirculation. That means flow can go out or come back. In some cases, similar to that, opening is a good option as a boundary condition. There is also one issue is this pressure. It's about loss coefficient. So this is like a porous media approach. You can define pressure drop. All you need to define a loss coefficient. So pressure drop will be added to this specified pressure. So I will give possible options for opening. You have seen similar screenshot for inlet. Now I'm giving for opening. These are the options. I mean, heat transfer only enthalpy is not allowed. Only subsonic flow can be defined. The other rest is for mass and momentum. Turbulence options are similar to inlet condition. Here is also, I want to mention, in mass and momentum, we can define opening pressure or static pressure, then entrainment. So this is a terminology. This is I want to mention because in external flow, Fluent use far field boundary condition. This part is how we define far field boundary condition in CFX. Here is an example. You see this is a box. Maybe you might notice that there is a rocket inside of this tunnel. In CFX, inlet is given with the black arrow showing one direction. Also, this is for the outlet. You see also these blue arrows showing in both directions. That means this is the opening used for tunnel. And then I define the relative pressure as 0 and option for mass and momentum entrainment. This is another way of showing far field boundary conditions of Fluent. This is how you do in CFX. So let's talk about how do we define location of boundaries. Here is the rocket. It's a solid object we define as wall. Inlet and outlet is far from the solid object because of this pattern around this rocket. Ideal location, you see, this is the length. If I remember correct, it's 2 meters, and the length of the tunnel is almost 6 times it's long in a horizontal direction, 3 times in vertical direction. So this is this kind of long tunnel will allow flow to develop. Maybe this option, you see, suppose that boundary is somewhere here. I have shown this broken line. Of course, it is not the best option, at least better than poor location. Look at poor location is just behind the wake. So you see the flow is turning, so it's not good idea to put outlet or opening very close this vortex formation. So most probably case will not converge. This will just gives you an idea. Here is the definition of absolute pressure in CFX. Reference pressure plus relative pressure. Fluent user may know that reference pressure as operating pressure. That is the pressure defined inside of the model. But the relative pressure value is given in the when you give or set boundary conditions. So if you define, for example, reference pressure as 1 atmosphere, that means relative pressure will be 0. For example, static pressure is 0 at the outlet. In CFX manual, there are some hints about choosing well-posed boundary conditions. The first one, it says choose one of the boundary as either total or static pressure. So actually, I will give the list of possible options, but this is just recommendation from CFX. It says total pressure cannot be set at the outlet. You might know that total pressure is the summation of static pressure and dynamic pressure, so it's better to use total pressure at the inlet but not at the outlet. And another hint, if there is your outlet is open to atmosphere, so just use static pressure as 0 with the reference pressure of 1 atmosphere. The other one, if your inlet is open to atmosphere, use total pressure as a boundary condition. Here is the recommendation of CFX for possible options. At the inlet, you can define either velocity or mass flow rate. At the outlet, use static pressure. If you remember, the first recommendation was use at least one of the boundary condition as pressure. And here, outlet pressure is defined at the outlet, and this is it says this is the most robust selection. The second one, you can define total pressure instead of velocity and mass flow rate. At the outlet, velocity and mass flow. It says this is robust. Actually, usually we don't use, not common, but at least it is possible and robust. The third one, I think this is widely used. You define total pressure at the inlet and then static pressure at the outlet. So it says if you give meaningful initial values, program will converge. This is according to my experience for microchannel flow. you don't know what is velocity or mass flow rate, but only the pressure values available, then this third option is possible. And the fourth one is not recommended at all. So you define static pressure at the inlet and outlet, no information about velocity. Of course, the results will not be reliable, because when you define velocity and static pressure, as in the case of the first case, then program will calculate both velocity at the inlet and check the pressure at the outlet. Now, let's see some information about the turbulence. Actually, this lecture will not go over all the details, but at least I want to explain the first three options, because program will ask you to give some percentage. For example, low intensity as 1%, for medium, for high. So what are those percentages? Let's see. This is another screenshot from the textbooks, CFD textbook I suggested. You see velocity versus time plot. Velocity, you see the instantaneous values of velocity. It fluctuates around the mean value. If you add two of them, you will get values of velocity with respect to time. So turbulent intensity defined values of instantaneous values over mean velocity. So program will ask you whether your case is high turbulence, medium or low turbulence. So CFX or other books give some recommendation. For example, if you simulate turbine or compressible, that means you have high turbulence case, use between 5 and 20. If you if you simulate ventilation flows, use between 1 and 5%, and low cases like flow over car, maybe you can define 1%. So you can go over CFD online for more information about how to define these values for your cases. Now, we finished boundary conditions. So I gave you some information. So I will start a CFX application. But before this, I have to give some information about this, just to remind you what we are solving. So this screenshot for open form. So this is our transport equation, the first term, unsteady term, convection term, then next. This is also known as advection term. On the right hand side we have diffusion term and source term. So our variable is phi here. It could be density, velocity, whatever solved. So the only thing I want to show how it is programmed in open form, finite volume method. It's written in C++, that's why you see these dots. And then ddt is the time derivative of 5. This is how it is. So you can at least have an idea how these equations are represented. You see, actually you are not coding, but using the related functions defined by open form. Some people think that if they use OpenFOAM, they learn CFD much better than using commercial software. In my opinion, it is open to discussion. Only a commercial CFD user should go over all the default values, so they should know that. If you know those things, that means you are not different than open source code user. So let's go our case, microchannel flow. Inlet is 100 bar. This is a large pipe, cylindrical pipe, and then a small narrow pipe. At the end there is a diverging converging nozzle. Outlet is 2 bar. So this is the 3D geometry. This is inlet, and outlet I define as opening. That's why you see this double-headed arrow. This plus sign shows a monitor point, so it's not related to the geometry. Here is the my mesh. I used ISOM CFX block structured grid. If you notice, there's a size functioning here. It is narrow at this part. You see in the middle there are large elements, and then it's getting closer, much fine around this nozzle. This is the hexahedral mesh. This is the 3D picture of the mesh. I have used OGrid here, maybe you might see. If you are not familiar with this CFX, I want to show you this tree. You insert the boundary conditions. So here I have inlet and outlet, and then 3 walls. I gave a name: pipe, nozzle, and inlet pipe. So if you remember, this is actually Turkish, but I will describe in English. Flow regime. You have to calculate Mach number, local velocity divided by the sound velocity. So you will define m value, whether you work in subsonic or sonic velocity, because you have to define at the boundary. You see, this is my inlet. Program will ask you flow regime. I chosen as subsonic. Here is pressure. Do you see, this is a relative pressure. It doesn't say static pressure, but relative pressure is 100 bar. It has to be total pressure and flow direction normal to the boundary. I defined intensity as 5%. I think it's a good guess. Here is the outlet, opening, pressure, and direction. This is the name. Some people write here as dim, as dimension. It has nothing to do with this, but opening, pressure, and direction. This is I learned from CFX manual. It is 1 bar. You see, this is relative pressure is 1 bar. If you remember, outlet was 2 bar. And again, flow direction normal to the boundary condition. Here is the explanation. Absolute pressure is defined with a summation of reference pressure and relative pressure. Here I define inside of the model as 1 bar, and at the outlet the relative pressure is 1 bar. If you sum, it will going to add up 2 bar That's the outlet pressure. Inlet is the total pressure as 100 bar. These are the walls. I gave different colors to different sections of the geometry. This pink one is the nozzle. Here is how fluid model is done. This is an isothermal, that's the uniform density flow. I didn't do anything more, just selection of SST transport model. The rest is default values. For initialization, CFX gives some recommendations, so I will leave it to you. You can read if you will be CFX user after this lecture. Again, do you remember CFX was saying if you define total pressure at the inlet and static pressure at the outlet, you have to give good initial values, otherwise program will not converge. Here is the my initial guess. I gave very low velocity, 0.1. Now, how about solver settings? Here is again our transport equation. This is the advection term, so we have to discretize this equation. So program asks discretization scheme whether it is high resolution or first order. I will describe soon. This is a steady state solution, timescale control of CFX, actually relaxation parameters, and this is the residual I defined as 1 e to the minus 6. I will explain those things. Here is the advection term of the transport equation. We will apply actually not we, but CFX will apply finite volume method. It's going to discretized and then some correlation between inlet and outlet of control volume. Here is the equation, how a value in one node is related to the other. So think this box as a control volume in our system. Suppose that this is for velocity, so velocities are stored on the faces of the cells. So if you use beta as 0, that means velocity here in on the left hand side of the face will be equal to the right hand side of the face. That means the value on one face will not change. It will be transferred to the outlet of this cell, but there will be another cell next to this cell. That means this is the inlet to the other cell. So you can usually we leave it high resolution scheme. If we have a problem with the solution, we can use upwind because you do some averaging if you use a high resolution scheme. This is the definition of our residuals. This equations tells you a solution of variable phi. In a matrix form. Suppose that a discretization scheme is applied, so we will have a matrix with a lot of zeros and some values inside this matrix, and then you define some values on the boundaries. So if so this is in this array, So if you solve this one, that means the difference between right hand side and left hand side will be 0. But actually there will be residual. Think that this is also iterative, and many equations for many variables. So this R will be calculated statistically. That is, the square of residuals will be sum for all, and then it will be again one more square root. So this is actually 1 e to the minus 6 is the desired one, but if you reach the 10 to the minus 3, it's also possible. Here is, if you don't choose your relaxation parameters, that means program may oscillate. So you have to choose different options, solution options to get solution. So when people see this kind of fluctuations, they choose, actually not choose, they try to modify their mesh or some model settings. Before doing this, you have to know what will be your time scale while using CFX. Here is the residual plot of my case. I gave 1000 iteration, so it's actually, I should stop here. Anyway, I just leave it 100, so it reaches 1 e to the minus 6. So, but this is not enough to be sure to converge the equation. You need to define a monitoring point where you expect fluctuations. So I have chosen this point as a monitoring point, and then I get the value, that is the velocity at that point. Then I run the case 100 iterations more to see the variation of this velocity at monitoring point. If you see this, the scale is a single value, so more or less they are same, then I can say convergence is achieved. So residual plot is itself not good enough, so you have to choose a monitoring point or points to be sure your solution is converged, and some values shouldn't change with the iteration. Here is the vector velocity color contours. You see the velocity is very low in large portions of this geometry. Only there is a jet flow along the converging diverging nozzle as expected. This is much closer screenshot. Please pay attention. This is a geometry I created on my own to give a different shape to this nozzle. You see, these are conical part, and then there's a curvature around it. So this is how velocity, jet flow will move this curved conical shape. This shows the streamlines of this geometry. Now, we have seen that yes, flow is converged and parameters are not changing with number of iterations, but this doesn't mean that you shouldn't check your results. This is one more check. This is you see the pressure contours. I select a point to see what is the pressure. That is the 100th bar. This is the how I defined This was my inlet condition. That means program satisfied what I gave as an input. Always check inlet and outlet values, even you define on your own, because during the iteration, program may change those values. And this is again high pressure, low velocity, and then you see this is not a typical pressure pattern in diverging converging nozzle. Here is a screenshot. This is high pressure red areas, low pressure in blue areas. Because of the geometry, there is a sudden pressure drop. So this is a comparison of low velocity, actually velocity and pressure color contours. Maybe comparison of Bernoulli, because in Bernoulli, as you know, velocity and pressure is related to opposite to each other. That means if pressure is high, that means velocity is low. Just opposite in diverging section of the nozzle, high velocity means low pressure. So it is better to show this so that whatever you gave your report, people may not know the Navier-Stokes equation, but from undergraduate they will remember Bernoulli equation. This is also written in Turkish. I did this study actually for cavitation, because this presentation was for beginners, so I skipped multi-phase flow simulation details, but at least I want to show. You see, this is a vapor. It says water vapor fraction, volume fraction. Actually, this is the vapor of oil that I use as a fluid. But in CFX, instead of creating a new component, just I changed the values of water vapor, changed the, for example, the density and some coefficients. This is why cavitation occurs here, because of flow separation, and low pressure areas will be filled in oil vapor. Thank you. Here is the end of my seminar. I hope you found useful.